also talk about randomized protocols. So what does it mean? What do you mean by a randomized protocol? No, but how does the protocol change? Exactly. Now, my protocol will depend on X, Y, and some random coin tosses, right? And then the entire thing works out, and I have a cost with, for a particular R, the number of communication bits are fixed. And then this model is only advantageous if I allow some error, right? If I say that I'm correct only on most of the R's, not on every R, right? So the difference is, first, I have some random bits. My decision in my protocol can depend on random bits, and secondly, I can tolerate some error. With some probability, I can give a wrong answer. But what do I mean by probability in this case? What is the source of probability? What is the source of randomness here? Across R, right? So the case we are mostly interested in is the worst case. It is saying that probability over R protocol works correctly on X comma Y is greater than 2 by 3, and this holds for all X comma Y. This is one measure of saying my protocol works correctly. This is fine. Why 2 by 3? Any? Yes, any number greater than half works. Do you know why? Not Dev, anyone else? Just repeat it. You can reduce the error as much as you like just by constant number of repetitions. And in most of these cases, we are interested in the asymptotics. Is the number of bits exchanged n, square root n, log n, things like that. So constants are for free. So you can repeat it constant times and change it from 2 by 3 to 3 by 4 to 99 by 100. So this constant really doesn't matter until it is more than half. Okay, and more than half is clear, right? Because I can always succeed with probability half. My answer is 0 and 1. I just toss a coin and answer. Okay, good. This is the worst case communication error, or error in a communication protocol, right? And a very weak version is average case, where we have some input distribution in mind, okay? Not element, mu is a probability distribution on my input sets. I assume that my inputs are coming from some distribution. The most natural probability distribution is uniform, right? Pick X with equal probability from here, pick Y with equal probability from here, right? Every pair you pick with this probability. This is the most natural, but not the only one, right? So now in this case, what I want is protocol succeeds. Notice there is no X comma Y here. There is no for all X comma Y. Correct? And yeah, in complexity theory, we mostly care about worst case, but there are people who talk about, oh, we should talk about average case, things like that also. Let's not go into that discussion, but at least see that this is harder to satisfy, right? For example, if I am correct here, if I have a communication protocol with cost C, it works here, right? Then definitely it works for average case, every mu, right? That means average case cost is less than equal to worst case cost. Though this does not make sense, right? Because what do I mean by average case cost? I should say for all mu, average case cost mu is less than worst case cost. Sure, agreed? Do I need to prove this? Fine, right? If I succeed on every input, then I succeed on every distribution of input too. Right? Whatever be the distribution. Okay? Now, the great part. It says so this should ring some bell. You know, you should be agitated. How can this be true? Right? You see, this was a very, very strong condition to hold. I was saying for any input, I should succeed with probability 2 by 3. Here, I am saying, let's take this distribution. You need to only be correct with high probability on that distribution. Right? Think of what are the easiest distributions? Point distribution. So in some sense, this is saying you should only be correct on one pair of input x comma y. And then any distribution on that. So this seems much, much easier than that case, right? So obviously one thing is I am maximizing over mu. Right? What is the other thing here? This, when I am writing this, I have an f fixed. Given a fixed f, these two costs are equal. This mu is not independent of f. For a different f, a different mu will be difficult. So what this theorem is saying is, you take a function, the worst case complexity is equal to the average case complexity for a particular mu. So again, there is a hard mu for every f, and that mu depends on f. So given an f, there will always exist a mu such that the average case on that is equal to worst case. Why is it nice? Because giving lower bounds here is much easier than giving lower bounds here. Right? So ultimately you want to give lower bounds here. Remember, why were we studying communication complexity? Let's say you wanted to lower bound set disjointness. You want to say that this much amount of communication needs to be done for set disjointness. But this tells us, find a good mu for set disjointness. If I can prove that the average cost is high, then the worst case is high. And it turns out the average cost here, when I talk about average cost, I can actually reduce to only the deterministic protocols. I will come to that. You have seen that. You remember when we proved the minimax theorem, when we fixed x inside the min y, we said y need not be random. It has to be from the vertices only, or there is no distribution there. It's the same idea here. So this is, you see that it is already max here. This will become a min-max thing If I fix a mu, this distribution, the distribution on min, I can escape. Okay? And this will. So in this worst case, what I'm saying is, look at a protocol which communicates C bits, C or less than C bits. This is a valid protocol if this is satisfied for that protocol. Yes, for whatever R, for whatever X and Y, it should communicate only C many bits. Okay, let's consider that protocol. So the cost of the protocol is maximum amount of communication needed for X, Y, R. See, what happens is, if it is taking a lot of time on some R's, we said, okay, we'll just cut it after some time and let it give a random answer. We will have this probability less. Okay, so you need not worry about cases when for some R's it is taking a lot of time. I can just say I will cut out the protocol. So the formal way to define it is, first I define the cost of the protocol. A protocol is correct for F if this condition is satisfied. What is the cost of protocol? Worst case over all X, Y, comma R, how much communication it is doing. Now, what is the cost of a function? What is the communication cost of a function? The cost of the best protocol. For every function, there are a lot of protocols which is going to satisfy this. Right? I have defined the cost of a protocol. Right? So this is a correctness condition. Think of this as indeterministic case when you say, oh, this is an algorithm for function f, if your algorithm computes f correctly all the time. Right? This is the same thing, right? What is the complexity of sorting? You look at all the algorithms which perform correctly on sorting, take the best algorithm there. Now your notion of correctness has changed. Nothing else. This is the notion of your correctness. Look at the best protocol which is correct on the function f. So once again, the definition of correct I am changing. That's all what I have changed. Okay? And like before, how much cost? Cost in the worst case. Whatever be the input, whatever is the maximum time I am taking, maximum communication I am doing, that's the cost of the protocol. Yes, for all xy, I look at my protocol, I check this condition. For all xy, am I outputting the correct answer with high enough probability? If I am, then I say that my communication protocol is correct for this function f. Okay? So, other way now, when I give a lower bound, it will basically say that if you take a communication cost, let's say I prove a lower bound of c. I'm saying if you take any communication protocol with cost c, there has to exist an input x comma y such that this probability is less than 2 by 3. Okay? Sounds good? Do I need to repeat? These are all, coming to the same point through here and whatever, right? But yeah, this is how I want to be correct, and then I optimize over all possible algorithms or protocols. Instead of algorithms, we have protocols now. Probably I should raise. Cost is and probably you might wonder why things are like this. This is not the only way to define correctness. This is what we generally call Monte Carlo way of defining correctness and randomized. There is another thing which is where we say Las Vegas kind of correctness, where the cost is expected cost over randomness. Okay, so there probably that is where your intuition will match more, Kumar. You have different cost for different randomness, and you can say, oh, even if there might be some R's for which I am taking a lot of time, but in expectation on a particular input xy, my cost is small. That's another model That's called Las Vegas model of randomized complexity. There also there is a maximum theorem, by the way, but we are doing it in the Monte Carlo. And don't ask me why it is Monte Carlo and why it is Las Vegas. I don't know. Except both are betting places which are related to probability. But right? So we want to prove this, right? And we already see a maximum structure. So this is going to be protocols. So this is a distribution over inputs. Correct? And the same cost here. This is just the idea. Okay, so we have to come up with something here so that these things make sense. This almost looks like average case complexity. This will become worst case complexity. This also looks like worst case complexity. I am minimizing over protocol for any distribution. Remember, if I fix now protocol here, max over mu is max over only the vertices. So this is saying max over xy, some cost. So this looks very close to what we want to do. So now, what do we do?